Chapter 14, Multiple Integration, and section 14.1 is the iterated integral and area in the plane. So an iterated integral is just basically taking integrals of integrals. So let's write that down. We are taking integrals of integrals, and obviously it's a little bit more complicated than that, but that's the big idea. We're taking an integral of another integral, and we work from the inside out. So we're going to work that inside integral first, then work our way out. Okay, so what does this mean? It means that if I have an integral of some function of xy, right? And I want to take that integral with respect to x first and then take that integral with respect to y. What I'm doing is I'm going to take this integral first, find out whatever that is, so that'll give me some capital f of xy plus, and I'll explain this in just a moment, some small function that is constant with respect to x, so some small function of y. And then we would take the integral of this with respect to y. So where is this little constant function coming from? Well, it's coming from the fact that if I were to take the partial derivative with respect to x of some function like this, like let's say x squared y plus 2y, then when I take the partial derivative with respect to x, we get 2xy for the first term, but the second term does not contain an x and it goes to 0, right? So when we take the antiderivative, we have to account for any possibility of there having been a function of y that did not contain any x's being a part of the original function. And when we take that antiderivative, we should get things that match. So for example, if I've got f of xy equal to x squared y, we'll just use that again. Then if I take the partial derivative with respect to x, I get 2xy. If I take the partial derivative with respect to y, I get x squared, right? So if I were to integrate fx with respect to x, I should get the same thing that I would get if I integrated fy with respect to y, right? Because they're going back to the same function. If I start with the same function, I take the derivative with respect to x. If I integrate with respect to x, I should go back to the original, and the same thing with respect to y. The only problem is there could have been constant terms out here, so what I'm going to do is I'm going to account for those by adding that constant function. And we say constant, it's not a constant function as in a real number constant, but it is constant with respect to what we're integrating with. So plus a constant function with respect to x of y. So c of y, and here we have c of x. So I'm going to put c1 and c2 because those functions do not have to be the same function. But the idea is if I integrate with respect to x, I add a constant function with a function of y. And if I integrate with respect to y, I add a function of x. So that's worth writing down. Let's do that. So if we integrate with respect to x, we are going to add a constant function of y, so a function of y. If we integrate with respect to y, we want to add a function of x. All right, so let's do an example of just a basic integral here. So let's integrate cosine of xy with respect to x, okay? So again, the y is going to be held constant for this exercise. Then we've got to see here, so cosine of xy, I'm going to do a u substitution. This was a common error on the previous exam, so I want to make sure everyone sees what's going on here. I'm going to let u be equal to xy, then du is equal to y dx, which means dx is equal to du over y. Oops, got a little excited there. Du, there we go. Okay, so I'm going to make the appropriate substitutions. So this is going to be the integral of cosine of u, and dx gets replaced with du over y. So I'll just put the 1 over y out front and put the du out here. Because du over y is just 1 over y du. Okay. All right, so the 1 over y comes out as a constant because it is not part of what we're integrating with respect to. We get cosine of u du. Well, the cosine of u is positive sine, so this is 1 over y sine of u plus our constant. We'll get to that in just a moment. U is equal to xy, so this is 1 over y sine of xy. Now we have to add our constant. We integrated originally with respect to x, here it is, so we're going to add a constant that's a function of y, so plus c of y, and there we have our antiderivative. All right, so let's do another example now. Let's do an actual double integral this time. The fact that there are double integrals, of course, intimates that there are, or insinuates that there are triple integrals and quadruple integrals and bigger and bigger and bigger integrals. So let's do a double integral. We have the integral from 1 to 2 of the integral from 1 to x. I can do better than that. 1 to x, there we go, of 2x squared over y plus 2y dy dx. Okay. All right. So the first thing I want to point out is notice that there is an x in the integral here. Okay. We're only allowed to have constants in our bounds of integration, in our limits of integration. So let's write some stuff down. So only constants or infinity may be part of the limits of integration. Okay, that's just a truth. That's something we have to deal with. So why is it then that I'm allowed to have this x here? Well, you may have noticed already that the interior integral is being taken with respect to y. X is constant with respect to y. So x may be in the bounds of integration if we are integrating with respect to y. Okay, and vice versa. If we're integrating with respect to x, y can be in those bounds of integration. However, the very last integral we take, the very outside integral we take, must have constant bounds of integration, because at that point, we're not going to be integrating anymore with respect to x or y. So we've got to have it set up in that way. Furthermore, and this we'll see more of later, but the bounds of integration can only contain variables. You know what? I'm not going to say that. Let's save that for another day. Okay. So to work this problem, we are going to find this internal integral first. Then we're going to put it back inside. So let's do this. So I'm going to do. I thought about getting creative. I'm not going to do that. So this is equal to the integral from 1 to 2 of. And now we need to start finding this antiderivative. And when we're done, we'll find that integral with respect to x. Okay, so we're integrating this with respect to y. So I've got 2x squared. Let me just rewrite this integral, 1 to x. This first portion here, I've got 2x squared. That's constant in this integral, times 1 over y plus 2y dy. So the only thing here that I'm really integrating is the 1 over y, because 2x squared is constant with respect to y for the purposes of this integration. So what is the antiderivative of 1 over y? Well, that's going to be ln of the absolute value of y. So this becomes the integral from 1 to 2 of our bigger integral. So now we're integrating. So I've got 2x squared times ln of the absolute value of y. That's the antiderivative of 1 over y. And then I need the antiderivative of 2y. So that's going to be add 1 to the exponent and divide, comes out to be y squared, right? Now, normally, if I were just taking an integral, indefinite integral, so I didn't have bounds of integration, I would have to add on a constant function with respect to x. But I don't have to do that here because we have bounds of integration. Any constant function with respect to x is just going to cancel away. So we are going to take this and evaluate it from 1 to x. Man, I just can't get that x to work today. Let's try again. There we go. And whatever I get there, I will then take that and integrate it with respect to x. So notice all of the y's are going to be replaced by x and 1. So let me do that. So x and 1 are going to replace only the y values. These are y values, right? If we're integrating with respect to y, these are y values. We do not plug them in for x's or z's or anything like that. We're just plugging them in for y values. Okay? All right, so let's do that. So we have then our integral here from 1 to 2 of, okay. So I've got 2x squared times ln of absolute value of x, making that substitution with x, plus x squared, minus, now plug in the 1, 2x squared ln of 1 plus 1 squared, and then we'll find that integral with respect to x. Okay. Okay, so this is our integral from 1 to 2 of 2x squared ln of x. We can drop the absolute values because our values on x are 1 to 2, so it's okay. If you're not comfortable doing that, just leave them there, that's fine. Plus x squared minus, now ln of 1 is 0, so that goes to 0, and then 1 squared is 1, so minus 1, and then we integrate this expression with respect to x, and now we're down to an old-fashioned integral that we would have seen in calculus 2. So the first thing I'm going to do is split this up. So we get the integral from 1 to 2 of 2x squared ln x dx plus the integral from 1 to 2 of x squared minus 1 dx. Okay, and this first one has to be integrated by parts. I say has to, it's really the best way to go. So integrated by parts, and I will be asking you for, exact answers on your test. So I'll need you to go ahead and do these integrals by hand. So we have integration by parts. That's the formula for that, in case you've forgotten, is the integral of u dv is equal to uv minus the integral of v du. So we'll pick a u and we'll pick a v. So to make this easy, we want to let u equal to ln of x because that has a very nice a very nice derivative, not a very nice antiderivative. So that makes du equal to 1 over x dx. And then dv, from our formula, we need a u and a dv, that'll be equal to the rest of it. So 2x squared dx, take the antiderivative, we get v is equal to 2/3 x cubed. Except that doesn't look anything like a 3. Let's try again. Get out of there. All right. There we go. 2/3 x cubed. And then the rest of this, this integral over here is a very straightforward polynomial integral, so that won't give us any trouble. Okay, so let's go ahead and use the formula. So this is going to be equal to the integral from 1 to 2. Use the formula. All right, so we start with uv. All right, uv, so that's ln of x times 2/3 x cubed. So that's, I'm going to put the 2/3 x cubed in front. Okay, and then this is being evaluated from 1 to 2. Those are the bounds of integration on x, so it goes from 1 to 2. Minus the integral from 1 to 2 of v du. So that's 2/3 x cubed times du is 1 over x dx. Okay, plus the remaining integral from which is the integral from 1 to 2x squared minus 1 dx. Okay, so let's go ahead and work through this. So 2/3 x cubed ln x evaluated at 2 and 1. That's going to be 2/3 times 2 cubed times ln of 2 minus 2/3 times 1 cubed times ln of 1. All right, so ln of 1 is going to go to 0. ln of 1 is 0, so this entire term is going to go to 0. And then we would finish it out minus da da da. So this comes out to be, let's see, 2/3 times 2 cubed, that would be 8 times 2/3, so that's going to be 16/3. ln of 2 minus the integral from 1 to 2 of 2/3. Now we get a little simplification here. X cubed divided by x is x squared, and that's valid because 0 is not part of our bounds of integration. So this is going to be x squared dx plus the integral from 1 to 2 x squared minus 1 dx. So let's go ahead and evaluate these two integrals. Okay, so we get 2/3. Well, if I add 1 and divide, it becomes 2/9, right? So 2/9 x cubed, evaluated from 1 to 2, plus 1/3 x cubed minus x, evaluated from 1 to 2. All right, so let's crank through this. All right, so here we're going to have 8/3 minus 2, so 2 is 6/3, so 8/3 minus 6/3 would be 2/3, minus 1/3 minus 1 would be negative 2/3, so that becomes plus 2/3. So then we've got 16/3 ln of 2 minus 14/9 plus 4/4, which is a total of 12/9. So I can get an LCD here. So that's going to be 16/3 ln of 2 minus 2/9. And there we have it. No need to add a plus c, constant function or anything, because this was a definite integral. So any constant functions would have canceled out during the process. So next we're going to look at finding area in a plane using the iterated integrals. So area in the plane. Okay, so to set this up and to look at this from the context of an iterated integral, we're going to use the fundamental theorem of calculus. So check this out. So we know if we have got, a couple of curves in space, let's say I got that one and maybe that one, and I'm interested in knowing what is the area between these two curves from x equal a to b. If my first curve here is g of x, let's say g1 of x, and this one's g2 of x, then I know that I can set this up and find that the area of this red region here is equal to the integral from a to b of g1 of x minus g2 of x dx, right? Well, according to the fundamental theorem of calculus, this right here is really just the integral from g1 of x, g2 of x, back that train up, to g1 of x, evaluated with respect to y, right? So just from the fundamental theorem of calculus, because we know that this is going to be equal to g1 of x minus g2 of x. And then we put our iterated integral on top of that, and that's what we get. So this is what we're finding, this is our iterated integral for finding area. And that may seem like an extra step, like why are we doing this? We already know how to find this area, but it actually is going to set itself up really nicely for our application problems. So let's go ahead and just do a couple of examples. Actually, before I do that, let me just write this down. Our area between these two curves is our integral from a to b of the integral from g2 of x to g1 of x dy dx. Okay, so let's do an example where we find the integral, the area represented by the integral. So we're going to sketch it and we're going to evaluate it. So let's say sketch the region represented by the integral and find the area. All right, so here we go. We have the integral from 0 to 4 of the integral from 0 to square root of x of dy dx. Okay, so clearly this is area in a plane. I don't have anything else going on here. I've got nothing in the nothing in the integrand other than 1, right? So this is just a straight up region in the plane, and we're going to figure this out. Now, how in the world are we going to do that? Well, I'm going to tell you. First thing to notice is it's the outside integral that we're taking with respect to x. So this is an x value, and this is an x value. Okay, the inside integral is being taken with respect to y. So this is a y value, and this is a y value. There are the boundaries for our region in this plane. So let's go ahead and sketch those. So let's see here. We've got x from 0 to 4, so this is x equal to 0 here, and I'll put x equal to 4 here. Okay, then I've got y equal to 0, which is of course here, and y equal to the square root of x. Well, the square root of 4 is 2, so that'll be about there, and it's going to look like this. And so this is y equal to the square root of x. So this is our region right here. So there's the sketch of our region. Now, to evaluate this integral, we are going to work our way from the inside out. So this will become, get back to white, there we go. So this will become the integral from 0 to 4 of, by the fundamental theorem of calculus, the square root of x minus 0 dx. And this, the integral from 0 to 4 of the square root of x dx, is exactly what we would have set up if we had been given this picture and said, find this area. We would have thought, oh, well, that's just the area under the curve from x equals 0 to 4. And that's exactly what we ended up with. Okay, so we add 1 to the exponent, so that exponent becomes 3 halves, divide by 3 halves, so we get 2/3 x to the 3 halves, evaluated from 0 to 4. So 2/3 times 4 to the 3 halves, minus, plug in a 0, we get 0. So 4 to the 3 halves is going to be 8, so that's going to be equal to 16/3. And of course that's units squared, whatever those units happen to be. So in an application problem, if we were given measurements, we would have to use the same units and keep our units straight. Okay, so what if we wanted to change our order of integration? What if I wanted to integrate with respect to x first? So let's do that. Let's change the order of integration. So instead of thinking of this as the area under the curve y equal to square root of x, I'm going to think of this as the area to the left of x equal to 4, and we're going to have to figure out how to make that work. Okay, so I'm going to integrate now first with respect to y, first with respect to x, then with respect to y. So we're going to change this up so that we're first integrating with respect to x. So let's see if we can figure that out. What's going on here? Well, if I look at this from a strictly x perspective, I'm moving from the curve to the line x equal to 4, right? So my upper boundary is 4, because that's as high as x is going to go. And my lower boundary for each of these green rays that I've drawn here, my lower boundary is going to be the curve y equal to square root of x. So this is going to be 4 on top and y equal to the square root of x on the bottom. Trouble is, this is taken with respect to x. I can't have x as part of the boundaries, as part of the limits of integration, because we are integrating this with respect to x. So we have to do a bit of manipulation. If y is equal to the square root of x, that implies that x is equal to y squared. So that is going to be our lower boundary, y squared. Oops, there we go. All right, so we are evaluating this from y squared to 4, so that's going to be in our x direction. Then from bottom to top, our boundaries on y is just going to be constant values, right? I can't have any functions going on in the external integral, the very outside integral. It's got to be just constant values. And so y is going to go as low as 0 and as high as 2. And so there we have our integral. So now we can get that set up. So this is going to be the integral from 0 to 2 of, and by the fundamental theorem of calculus, this middle integral just becomes 4 minus y squared. We integrate that with respect to y. So this is the integral from 0 to 2. Might want to take the integral, huh? So this is going to be 4y minus 1/3 y cubed, evaluated from 0 to 2. So we plug in our 2, we get 4 times 2 is 8, minus 1/3 times 8. minus, plug in a 0, we get 0 minus 0, 0. So this comes out to be 8 minus 8 thirds. So that's 24 thirds minus 8 thirds for a whopping grand total of 16 thirds. So as you can see, it does not matter which direction we kind of focus on for taking this area, for finding this area and taking this integral, it's going to come out to be the same either way. So as long as it's set up correctly, it will come out to be the same either direction. So let's do another example then, where we have to find an area, but do by splitting up our region a little bit. So let's take a look. So find the area of the region bounded by y equal to 4x minus x squared, the x-axis, and the line y equal to negative 3x plus 6. So the very first thing you should always do with these is sketch them. So we definitely need to get these sketched. We need to know where these things are going to intersect. So we need to know where the zeros, that's where it's going to intersect the x-axis. We need to know where the two y functions are equal to each other. And then we can get a good accurate sketch. So 4x minus x squared is equal to 0 if, let's go ahead and factor it so we can see, x is 0 or x is 4. And then negative 3x plus 6 is equal to 0 if x is equal to 2. Okay. Then where are these two equal to each other? We've got 4x minus x squared is equal to 3x plus negative 3x plus 6. So let's get all this on one side. Okay, so that'll factor nicely. So x equal to 6 and x equal to 1 is where they're going to intersect. So now that we have all that information, we can sketch this region. Okay. Okay. So the intercepts for 4x minus x squared are 0 and 4. All right. The y-intercept for our line is x equal to 2. You know what? I should probably color code these. Let's make this one 4x minus x squared. Let's make that one green. Okay. So now the vertex of that point is going to be at 2 because that's center between 0 and 4. So plugging in a 2, I get 8 minus 4 is 4. So we need to go up to 4. And there's our vertex. And this is going to be a parabola opening down that looks something like this. Now we've got our line. So that line has a slope of negative 3. So that's going to be down 3 over 1 or up 3 back 1. So up 3 back 1, up 3 back 1. There's our intercept. So let's make that one yellow. So here's our intercept, intercept. And that's going to intersect our line at the point 1, 3. Right here. Okay, it's also going to intersect again over here at 6 something. As you can see, my scale's all off and wonky, but it doesn't matter because that's terrible. It doesn't matter. Wow, that was even worse. Let's try this one more time. One more time. Come down. But as I said, it does not matter because we're also bounded by the x-axis. So I'll do that in blue. So we're also bounded by the x-axis. And so the region in question is going to be this space here. So there's our region. All right, so as I said, we are going to have to split this region up. And the reason for that is it really just depends on how we want to look at it. If we want to go from top to bottom, right, like doing this integration with respect to x is our external integral, we would have to split it up right here. And the reason for that is because, well, theoretically, let me try that again. There we go. And the reason for that is to the left of this red line, the function on top of the region is the green curve and the one underneath is the yellow curve. But to the right of this line, we've got the green curve on top and the blue curve on bottom. So we can't just do this in one go. We'd have to split this up. The other thing we could do is we could try splitting it up horizontally. where we kind of check this from left to right. The trouble is in this upper region right here. Let's see if I can get a better circle there. On this upper region right here, we're dealing with a situation where it's parabolic. We would have to cut it in half, find this region to the right or to the left and double it. So that's a little more complicated. So I am going to say we should just go ahead and do the vertical integration where we have functions of x above functions of y, functions of x above functions of x, as opposed to functions of y to the right of functions of y. All right, so we are going to go ahead and break this up into two regions here. Oops, there we go. So we've got region 1 here and region 2 here. So we're going to set up an integral to get the area for each of those regions. So for region 1, we're going to integrate two integrals, dy dx, because we want to integrate last with respect to x, right? So we have our function of x, and then we're going to integrate that. Now, how do you set up your boundaries? Well, let's just take another look. Integrating first with respect to y. So I need my y values here and here. Well, y runs vertically. So how low does this region go? How high does this region go? So the lower boundary of this region is given by this line, y equal to negative 3x plus 6. So that's our lower boundary, negative 3x plus 6. The upper boundary is given by the parabola, y equal to 4x minus x squared. Okay, so there are our boundaries for y. Now we're going to look left to right. How far left does the region go in the x direction? How far right does the region go? So what is the minimum x? What is the maximum x? So we take a look here, and the region stops at this point. Well, that's where x is equal to 1. So our lower boundary for x is 1, and then x stops here on the purple line that I had drawn. That's going to be where x is 2. So how far left? 1. How far right? 2. So here we have it set up. Now we'll do the same for region 2. So region 2, integral, we'll integrate with respect to y first, then x. Now here, our boundaries on the upper and lower boundaries, I should say, so our boundaries in the y direction are going to be slightly different, because now the line negative 3x plus 6 is too low. We don't need that one. We're stopping at 0. So our lower boundary on y is 0, and remember these are y values. So our lower boundary on y is 0. Our upper boundary is the parabola again, 4x minus x squared. Now on x, the region R2 goes as low as 2 and as high as 4. So that region, x values run from 2 to 4. So we set that up. Now, all we have to do then is find these integrals and add them together, and that is our total area. So the total area is R1 plus R2. So that's going to be the integral from 1 to 2 of the integral from negative 3x plus 6 to 4x minus x squared dy dx, plus the integral from 2 to 4 of the integral from 0 to 4x minus x squared dy dx. Okay. All right, so let's do this integration. So this becomes the integral from 1 to 2 of 4x minus x squared minus negative 3x plus 6 dx. And again, that's just the fundamental theorem of calculus at work. 2 to 4 of 4x minus x squared minus 0, so I can just stop there. Okay. And let's simplify the first integral. So we've got 4x minus negative 3x is 7x minus x squared minus 6 dx plus the integral from 2 to 4 of 4x minus x squared dx. So let's integrate both of these and evaluate. Okay, so we have 7 halves x squared minus 1/3 x cubed minus 6x evaluated from 1 to 2, then 4x squared over 2 minus 1/3 x cubed evaluated from 2 to 4. So let's go ahead and plug these in. I can do a little bit of simplification here, so that'll be 2x squared there. All right, so plugging in a 2 into this first batch, we get 7 times 4 over 2 is going to be 14, minus 2 cubed is 8, so that's 8/3, minus 2 times 6 is 12. Okay. Minus, now we plug in the 1. So 7 halves minus 1/3 minus 6. Okay, We add to that. Now we're plugging in the 4. 4 squared is 16 times 2 is 32. Minus 4 cubed is 64, so 64 thirds. Minus, plugging in the 2, we're going to get 8 minus 8 thirds. All right, so we can simplify this. 14 minus 12 is 2 minus 8 thirds. So that's 6 thirds minus 8 thirds is negative 2 thirds. Minus 7 halves minus 1 third minus 6. Okay, so 7 thirds, that's going, or 7 halves rather, that's going to be 21 sixths minus 2 sixths minus 36 sixths. So we've got 21 minus 38, which is going to be negative 17. Yeah, I think that's right. So negative, get back to my color here. So that's going to be negative 17 over 6 plus, okay, 32 becomes 96 thirds minus 64 is 32 thirds. So that's 32 thirds minus 8 is 24 thirds minus 8 thirds is 16 thirds. Okay, so what do we got here? Negative 2 thirds plus 32 thirds minus 16 thirds. That's going to be 14 thirds. So this is 14 thirds minus 17 sixths. 14 thirds is equivalent to 28 sixths minus 17 sixths. That's going to be equal to 11 sixths. But wait, I just saw an error that I made. Did you guys catch it? I hope you did. This is actually incorrect because this is incorrect. We need to adjust that sign. So let me get rid of all of this. Subtracting a negative creates a positive. We all know that. So this is supposed to be plus, because we have minus a negative there, right? So that's plus 17 sixths. So that's going to be, 30, okay, LCD, 28, there we go. Okay, hold on, give me a minute. 28 thirds plus 28 thirds. See, that's what I'm, slow down a little bit here. See if we can figure this out. Okay, so we've got 14 thirds plus 17 sixths. So we need an LCD, so that's going to be 28 sixths plus 17 over 6. Can't add 14 to 17, silly. So then we've got 28 and 17, which is going to give us, what, 56? 20, 30, 46. 46 over 6, which will reduce by a factor of 2. Oh, guys. 8 and 7 is 15, yes? Okay. This is my last example for this one, and thank goodness for that. So 45 over 6 has a common factor of 3, so we can take out a 3, and what do we get? We get 15 halves. Now, let me double check that that's correct. That is correct. Thank goodness, we're there, we're done. Put a dot on it, finished. Okay, that is my last example for this unit. When it comes to setting these up, you're looking for what's easiest. Is it easiest to first go left to right, and then just throw in constant numbers for the y values, or is it easier to go from bottom to top and then throw in constant numbers for the x values? So setting these up, there's no wrong way to do it, but there's usually an easier way to do it, and I recommend finding the easier way. But if you do it correctly, you can do it either direction. Yeah, and as always, if you have any questions, do please let me know.